In order for something to be an aromatic compound, it must follow these four things. It must be cyclic with conjugated pi bonds. Each ring atom must have an unhybridized p orbital. Unhybridized p orbitals must overlap to form a continuous ring of orbitals. And lastly, and most importantly, delocalization of electrons must lower the energy. When people say aromatic compounds, mostly they think of cyclic ring systems with conjugated double bonds, which is the criteria of the first three things. But the last one is often not met with these kind of things. So when people think of aromatic compounds, generally think of benzene. Benzene is a ring. It has unhybridized p orbitals on each one of the carbons. They are able to overlap and form a continuous ring of orbitals where the electrons become delocalized, and that's what gives it its aromatic characteristics. Aromatic does not mean cyclic ring with conjugated double bonds, although it is a requirement. What defines an aromatic compound is unusual stability. And in order to get that unusual stability, these first three things must be met. So with aromatic compounds, there are three types. There are aromatic compounds, non-aromatic compounds, and anti-aromatic compounds. Aromatic compounds are the compounds that have unusual stability. Non-aromatic compounds don't have significantly more stability or less stability. They're basically unaffected. And lastly, the anti-aromatic compounds are those compounds that follow these first three things, but actually are more unstable that way. So benzene is an example of an aromatic compound. This ring is more stable than this. So this has conjugated bonds, but in this case, it has one extra bond between these two carbons, which allow the p orbitals to overlap into a continuous ring, which thereby allows the electrons to become delocalized, granting it its stability. In other examples, like this one, four-member ring, it does the same thing, but in fact it is less stable than it would be if it were just open like this. And then there are plenty of other examples where it just doesn't make much of a difference either way. So let's have a look at an energy diagram to give a better idea of what being aromatic is all about. So it's important for it to be conjugated, cyclic, have overlapping p orbitals, but that's really just the means to the end, and the end being a more stable overall compound. So looking at this energy diagram, we've got a series of cycloalkenes, and what we're going to do is look at what happens when these bonds are hydrogenated. All of these things are going to be hydrogenated to the same end product, and what we're going to do is look for how much energy is released when this happens. So in the first example, we have a cycloalkene with one double bond. When this is hydrogenated to cyclohexane, it releases 120 kilojoules per mole. So if there's no special stability, what we would expect is that each pi bond to release 120 kilojoules per mole. So if we have something with 1, it's going to release 120 kilojoules. Something with 2 double bonds, it's going to release 240. Something with 3, 360. So going along to the next example, here is a cycloalkene with non-conjugated double bonds. So they're not able to confer any kind of special stability to each other that we know happens with conjugated systems. When this is hydrogenated, 240 kilojoules of energy is released just as expected. It's not until we get to a conjugated system, here 2 double bonds, but they're right next to each other, so they have some stability about them that the other ones don't have that we learned previously. When this is hydrogenated, only 232 kilojoules are released, so less than in this system over here, which implies that there are 8 kilojoules per mole of stability given by the fact that these bonds are conjugated. Now moving to the last example of benzene, what we expected before was there to be 360 kilojoules per mole, because there are 3 double bonds, and if there is no stability, which there is, but if there wasn't any stability, that's what we would expect. So when this is hydrogenated, what we find is that 208 kilojoules per mole are released. So in fact, this is more stable than the 2 pi bond system. It actually takes energy to break the first bond to get to something like this, and then the rest of it is exothermic. But 150 kilojoules per mole of energy is saved by it being in this formation and it being an aromatic system. So this essentially comes from the fact that you have all of these p orbitals. They're able to overlap with each other, creating basically just a big orbital where the electrons can delocalize. So because of that, it is a lot more stable than something else. Something that would be non-aromatic, it would be 360 kilojoules per mole if it were non-aromatic. And there are plenty of compounds that are like benzene, like an 8-member ring. It doesn't have any special stability. It's just normal. It would be, if it were 120 kilojoules for this one, then it would be 120 times however many bonds are in there. That's what would be released if it were non-aromatic. Something that would be anti-aromatic, it would actually be higher in energy than this, because it would be unstable. So that is what aromatic compounds are all about. They're not about just a bunch of conjugated double bonds in a ring. That's part of it. But what the result of that needs to be is a significant lowering in energy, as we can see in this energy diagram.